All right. Hey, everybody. Today we are doing topic 27, which is K-Nearest Neighbors, our second classification model we're hitting after logistic regression last week. As we get more into the weeds of classification algorithms, as a reminder, we have 3 study groups this week, today, not tomorrow, but Thursday, and then on Saturday. So a little bit spaced out, so it's every other day. Something to note is we're going to be hitting a lot of these classification algorithms. If you look on our homeroom, I put a summary of all the phase 3 models over here. It links to a Google Drive, same Google Drive that I have linked over here, by the way, the resources Google Drive. And this is in the phase 3 folder. And you'll see that these are all of the models that we're going to hit during this phase. Again, I do want to say that you don't have to go through all of the material of the phase. The most important things that I hope to get across are how to use classification models and how to evaluate them. You'll see today as another example, implementing them exactly the same for every single model. Of course, some of them have have details that are more important than others. Of course, that is all here on this handy dandy sheet. But yeah, it is not feasible for everyone to understand every single model by the end of the phase. It's very, very unlikely that even for me, that didn't happen. So yeah, as long as you're aware of that, you won't get burned out, hopefully. So yeah, just wanted to let you all know that this is here. Other resources that I didn't really talk about before. These are 2 books. They're pretty much the same. The content is the same, just that Introduction to Statistical Learning is the go-to book, and Elements of Statistical Learning, the books actually look very similar. Elements of Statistical Learning is a little bit more advanced if you feel very comfortable with reading math equations. For me, after I went through Flatiron School, I went through the first one, Introduction to Statistical Learning, and that really gave me a good foundation for a lot of the models and explaining how each of them work with like gradient descent, their different cost functions, so on and so forth. So I super recommend that one. Also, StatQuest has a machine learning playlist that I really do recommend as well if you want more bite-sized video explanations with a lot of nice graphics. That's a really good playlist to go through. And you'll see in the playlist a lot of similar algorithms that as we go through. So for example, well, we talked about cross-validation, confusion matrix, bias variance trade-off, a little bit of recap from the end of last phase, and also linear models, which includes, I believe, might include, oh, logistic regression is down here. Linear models is our linear regression. And it keeps going down. You see Ridge and Lasso, PCA, which we're actually going to hit next phase. But we have decision trees down here, naive Bayes, that's actually Thursday's topic. Decision trees over here, decision trees, that's what we're going to hit on Saturday. And then random forests, gradient boosting, that's the following week. Support vector machines is also another one that we do. So there's a lot in there. Neural networks is in this playlist as well. And neural networks is actually the end of phase 4. So this is a really, really nice, useful playlist. Each video is like maximum, well, this is saying 20, but around 15 minutes long on average. And they're really good bite-sized videos to go through. A lot of my former students really like this resource. So here for you in case you want it. Cool. So again, if you check out the calendar, there are a few events coming up there really interesting. The one I want to point out is Raphael is a guest speaker on Thursday. I think it will be recorded. I will make sure to get that recorded for you because I know a lot of you all can't make this time. But Raphael actually used to be an instructor at Flatiron School like myself and is now a data engineer. And I've spoken to some of you who might be more interested in like the data engineering aspect of data science. Is basically more about like building pipelines, so on and so forth. So that would be a really interesting one to attend. And I guess none of you are women identifying here, but there is a women's panel on Thursday evening as well. Also tomorrow, I'm doing a webinar on recommendation engines. Again, it's not necessary to go because it's pretty much the exact same content. It's a study group I'm going to give you all in phase 4. But in case you wanted to get a sneak preview, that is happening as well. The links I posted to your Slack channel last week, I think. All right, with all of that information out of the way, thoughts, questions before we get into today's material? Okay, let's get started then. So today we're talking about K-nearest neighbors, and K-nearest neighbors is kind of like a class of algorithms. So K-nearest neighbors can be used for classification. That's what we're going to talk about today, but can also be used in many other different ways. If you just think about how you can apply the concept of nearest neighbors, we'll talk about that in a little bit as well. You'll see that this algorithm also has a regression counterpart. So we'll talk about the classification. We'll use a classification example, but there's also a K-nearest neighbors regression that exists. I just want to make this known to you all in case you decide to do a regression project for like your capstone or something. This is a model that you can try out. Okay, but first we're going to talk about distance metrics, and two main things we're going to talk about: distance metrics and then also the algorithm in itself. So first I want to talk about parametric versus non-parametric models. When we talked about linear and logistic regression, these are the only two models that we've spoken about so far. These are both parametric models, mainly because there were underlying assumptions that our data needed to fulfill in order for our models to perform effectively, or what's the word, consistently and reliably. So main difference between parametric models such as linear regression, linear discriminant analysis, that's something we'll hit in phase 4 as well, and non-parametric models, one of which is K-nearest neighbors, K-means, that's a phase 4 thing too. Oops. Decision tree, that's what we're hitting on Saturday, is that parametric models make certain assumptions of the underlying data distribution. That's why we had to do linearity checks, heteroscedasticity versus homoscedasticity checks, multicollinearity, so on and so forth. For K-nearest neighbors, and also pretty much, let me think about this real quick. I think every single model we're going to talk about from today onwards, non-parametric. So you actually don't have to worry about any of the data assumptions before applying it to the model. And you'll see that because of that, not many people choose to implement logistic regression for the classification project, just because you have all of these assumptions that you have to work on fulfilling first. So basically, as I was mentioning, non-parametric models allow us to apply the models to data that are not normally distributed, or whatever the other assumptions are. So therefore, if assumptions of your data is not met, you can use non-parametric algorithms. So in a lot of your linear regression projects, a lot of the assumptions were not met. Maybe instead you can run a K-nearest neighbors regression. Or I think Ridge and Lasso still has assumptions as well. But yeah, all of the algorithms, a bunch of the algorithms we're going to talk about this phase have regression counterparts that you could potentially try and apply to your phase 2 project just to see how it does without needing to fulfill assumptions. So in terms of terminology, an important note, we only say whether our models are parametric, not our data. So K-nearest neighbors, non-parametric models. So far, the only parametric models that we've dealt with are linear regression and logistic regression. Okay, that's kind of just a terminology thing. Never been asked this in an interview before, but just good to know. So to start, as we're getting K-nearest neighbors, the middle word nearest is something that is extremely central to the algorithm itself. So when you're talking about nearest, you think distance. So therefore we have to start thinking about distance metrics. And distance metrics, I think, is something that you can definitely tune and get more used to. Distance metrics is also something, as you get more and more advanced, you get to play around with a little bit more. But today we're just going to discuss some of the more basic distance metrics so that you can start thinking about how distance or nearest is being computed. Okay, so some fairly simple ones. First, we have Manhattan distance. So one way of thinking of Manhattan distance is moving through grids. So if you have point A here, point B over here, Manhattan distance is just the absolute value of x minus y. So basically is the sum of x minus y. So let's just say we have, let me draw some coordinates here. Let's say that this is 0.5, 5, and then this is 0.1, 1. It is just the absolute value of 5 minus 1 plus 5 minus 1. So with these coordinates, the Manhattan distance will be 8. So if you take any of these lines, well, the red line, the blue line, or the yellow line, same distance. The only different one will be the green line because that's diagonal. And Manhattan distance, you don't think about diagonals. Cool. So that is Manhattan distance, probably the most simple distance metric that you can use. Here's just a NumPy example. If you have point A, 2, 4, point B, 1, -1 and 5, Manhattan distance ends up being 4 because 2 minus -1, so that makes 3, and then 4 to 5, that's 1, that makes 4. All right, so Manhattan distance, fairly straightforward. Any questions at any point, feel free to interrupt. All right, next we have Euclidean distance, and Euclidean distance is probably the most commonly used distance metric. And to calculate it, it is pretty much Pythagoras' theorem. So instead of taking the absolute value, you are taking the difference squared. And Euclidean distance looks like this typically, but it does scale up. If you have more dimensions, you still take the square root of the difference of the sum of squared differences between point A and point B. So very, very similar. All we're doing is instead of plussing the absolute there, we're adding the square of the difference. So with that, Euclidean distance gives us 3.16. So you can see that with this example, Manhattan distance ends up being a little bit longer than Euclidean distance typically. However, within an algorithm, it's important to note that they're always using the same distance metric, so they're always comparing apples and apples, oranges and oranges. Is really only in when you have a lot of features and a lot of different distributions of data that you start to get slightly different results when you use different distance metrics. Cool. More generalized than Euclidean distance, you have Minkowski distance. And it actually is, Euclidean distance is a subset of Minkowski distance, or Euclidean distance is a type of Minkowski distance. Because if you look at these formulas over here, I know it's kind of small. Let me see if I can zoom in a little bit. The main difference is with Euclidean distance, you are raised to the power of 2, but Minkowski distance, you're raised to the power of whatever number you want. So Minkowski distance, you can raise it to the power of 3, 4, 5, 6, 7, whatever you want. And Euclidean distance is always to the power of 2. So Minkowski distance, you can basically plug in 2, and that will be equivalent of Euclidean distance. But just so you know. Cool. Any questions about distance metrics? All right. Now, conceptually, if 2 points have very, very small distance between them, how this algorithm and this group of K-nearest neighbors algorithms are going to see these 2 points, you're just going to see these 2 points as being very similar, right? Because if 2 points are just close to each other, that's the way that these set of K-nearest neighbors models understands as being similar or near neighbors. So near neighbors are basically similar data points. So let's get to the algorithm. So KNN is simple, non-parametric, and lazy algorithm that can be used, as I mentioned, for both regression and classification. Non-parametric because it doesn't make any assumptions of the underlying data distribution, and is lazy because it actually doesn't learn a discriminative function, but actually memorizes a training data set. So what's really interesting about this is, I know we've talked about, and this is still considered a machine learning algorithm. This is kind of not using machine learning at all. What K-nearest neighbors is doing is actually just saving a bunch of distances in between data points, and we'll see how that's being done. So what the algorithm does is it ascribes class membership based on the closest K neighbors to the testing observation concern. And it's called K-nearest neighbors. The letter K is something that you can actually vary. You know how like an alpha, when we were doing ridge and lasso, we could vary our alpha. You can actually vary K. And KNN is a similarity-based algorithm, and the class membership of the observation depends on feature similarity to the training observation. So kind of like what I was alluding to before, if you're a nearer neighbor, you are more similar. So let's just use this as an example. So let's just say that in your data set, you have blue squares, red triangles. Those are your 2 categories of data. And you have this new example, this new green circle over here, and you want to classify this green circle to be either a blue square or a red triangle. So first, let's just think about, let's see what these, to explain what this diagram is saying. You have K equal to 1. When you say K equal 1, it means you're going to consider your 1 nearest neighbor. In this scenario, the 1 nearest neighbor to the green circle is this blue square over here. And so based on that, you're actually going to classify the green circle as a blue square because the point closest to the green circle is a blue square. And because these distances and where these are placed in this diagram are based on feature similarity, we can make that assumption. Now, if we change our k to be k equal to 3, we have this wider circle over here, and our 3 nearest neighbors include this one blue square, but also now these 2 red triangles. So now you can see that some sort of voting has to take place because it's not all the same shape. Now at this point, you would have to say, okay, we have 2 triangles and 1 blue square in our vicinity. What should we classify the green circle? By default, it will actually weight each of these as equal, saying that, all right, the blue square gets 1 vote, each red triangle gets 1 vote. This data point will actually now be classified as a red triangle. So depending on what k value you use, you can actually end up with a different classification of your data, especially if, you know, it's kind of like in like a gray area where there are data points of either class. Questions about like just conceptually how this algorithm is working? Cool, awesome. Yeah, I think it's pretty straightforward too. So yeah, as mentioned above, similarity does depend on the distance of observations from each other, which can be calculated using any of the distance metrics mentioned above. So commonly used one is Euclidean distance, as I mentioned. However, which distance metric you use, as well as the value of k, could affect the performance of your model. The decision boundary, I'm going to show you all decision boundaries in a little bit, can change accordingly to different values of k. All right, so now that we understand like the concept of how K-nearest neighbors is working, let's implement them and then we can get into more details. So we're going to use our iris data set again. That's the same one that was in the logistic regression notebook. And again, we have our 4 features and our target of 3 different irises. Cool. All right, so we are using our K-nearest neighbors classifier. And if you remember, we go through our steps. So first, we instantiate our K-nearest neighbors model. Let's just start with n neighbors equal to 1. Actually, let me open this up to show you all. So a bunch of different hyperparameters here. The most important ones, or the most important one, is probably going to be the number of neighbors, which by default is actually 5. And then other ones to note, I would say this is the other one that could be useful to note, is weights. Remember how I said before when you had like a voting system between the blue squares and the red triangles, each one got 1 vote in k equal to 3. You can actually weight it slightly differently. So if you are further away from the test data point, your vote is a little bit less has a bit less of a weight. So if you take a look at this, by default it is uniform. Uniform weights, all points in each neighborhood weighted equally, but you can also weight it by distance, where you weight them by their inverse of their distance. So if it's further away, it will be less important. Cool. All right, so back to this. Right now, we're just specifying n neighbors equal to 1. So we're just going to look at our 1 nearest neighbor to decide on the classification of our test data. So we've done this before with logistic regression. Let me just make sure this is run. Let's fit our x and y. We're not doing train test fit yet, but we'll fit our x and y. And you can see when we do our dot predict, we get an array of 0, 1s, and 2s. And then we end up with, hold on. We end up with our predictions, which are there. Here, I'll go through this process again later. Let me get rid of this for now. Okay, when we make predictions, this is making predictions on the X data set. Here, when we make predictions, we actually can use our X data. And what we can do is, hold on, sorry, this is a little bit out of order. All right, not a big deal. I'll come back to this in a little bit. Let's do this process first. We are doing our train test split, doing our scalar, fit our scalar and transform on our train and test, instantiate our n neighbors equal to 1 model, fit in our train set, predict on our test set. Cool, this is what I meant to do. Awesome. And based on this, we have our training confusion matrix and our testing confusion matrix. So as you can see with k equal to 1, we actually have perfect classification on our train set. And oh, turns out perfect classification on our test set as well. Cool, awesome. And also we take a look at our classification reports, which again, this should look familiar because all of this stuff was on our logistic regression notebook as well. All perfect scores across the board. So awesome. That's great. Okay. When we're doing any sort of classification model, again, I feel like I have to reiterate, I always want to see classification reports and confusion matrices for every model. So this is something that you're going to see over and over again. Okay, back to what we're talking about above. How does the dot predict work? So dot predict basically works on any array that has the same number of columns as your training data. So in this example, we fit it apparently on X and Y. And on X and Y, if you take a look at the shape of X is 150 by 4, which means you have 150 rows of 4 columns. So if you do dot predict on X, you take a look, oops. Hold on, make sure this is in the right order. If we do dot predict on X, if your X basically looks like this, right? So what dot predict is going to do is it's going to take each of these as a test data point and basically run it through the algorithm that it learned from the train set. So therefore, when we do dot predict on X, we should end up with 150 data points here. Cool, sweet. For making predictions, and here we want to talk about out of sample data. And this is going to be fairly useful when you get into your projects and you want to make a prediction function that can make predictions on anything. It can basically take in any array of numbers that matches the number of columns. So for example, let's just say randomly, I'm feeding it in 3, 5, 4, 2. And I think this is like petal length and width, sepal length and width, one of these. And then you can actually get a prediction, and this is class 2. You have to wrap it in double square brackets because it needs a 2-dimensional array rather than a 1-dimensional array. You'll actually see that if I were to take away this first layer of brackets, it'll say expected 2D array, got 1D array instead. You can either reshape using this, or pretty much what it's expecting is 1 row of 4 columns of data. That's how it gets that. So if I want to do another, if I want to make 2 predictions, I can do that as well. Cool. Questions about anything so far? I'm sorry, that's a little out of order. All right, okay. So next to talk about the hyperparameters. So here we can look at different values of K and also tuning the weights as well. So here I'm instantiating 3 different KNearest Neighbors model. N neighbors 5 with uniform, 5 with distance weight, 10 with distance weights. And with this, I'm just scaling my data real quick, and I'll talk about Scalar in a little bit. I'm going to scale my data and then plot my confusion matrix for KNearest Neighbors 1. Cool. So with 5 neighbors, and if you remember, our first pass at this was with just 1 neighbor. It changes our classification such that we end up with a bit of misclassification in the train set and still perfect test metrics. Now you might want to do this. Of course, this data set only has like 150 data points. This is when you start to think about bias variance trade-off. And I'll talk about that in more detail in a sec. But you can see that with these results, and if I were to change this to, for example, KNearest Neighbors 3, the results might be different. Okay, cool. With KNearest Neighbors equals to 3, we have completely different results. Again, no misclassification in our train set and 1 misclassification in our test set. Again, you're going to do more extensive testing than this, but just to show that changing the number of neighbors that you're looking at does change the outcome of your models. All right, and of course we have a classification report that you can look at. All right, let me lower this number so it won't take so long. Cool. So the main hyperparameter for KNearest Neighbors is the value of K, or how many neighbors you want to have in your that your algorithm is looking at to classify your data. So one way to do this, I'm actually going to show you all a much more automated way next week. But one way to go about this is just by looking at your train and test metrics with different values of K. So what we're doing in this for loop is we are running KNearest Neighbors with different number of neighbors from 1 to 20 with distance weights. We're going to fit it and append the scores for my trained and test set. By default, if we take a look at KNearest Neighbors, by default, if we look at the scoring attribute method, the scoring method will give you the mean accuracy. And for this purpose, accuracy works for us. If you remember from before, from last week, we talked about how there's also precision, recall, F1 score. You can get those as well. But anyways, for simplicity's sake, we're just going to use accuracy in this example. So when I run this real quick, it's basically already trained and tested 20 KNearest Neighbors models. And these are my train and test results. You can see that pretty much across the board, the train score is always perfect. But if you look at accuracy score, let's see why that didn't come in. Hold on. There we go. We want to have 20 here and 20 here. Okay. Cool. With this, you can see that after a certain point, the test doesn't perform as well. And we'll sort of see that why in a little bit. I'm going to talk about the bias variance trade-off and tuning the value of K. Here is where we talk about decision boundaries. So if you think about it, if for every test data point, you're only considering the one nearest neighbor to it, you can end up with a not very smooth decision boundary. For example, this over here. So let me zoom in over here. You can see that this is K equals to 1. And even though you have a bunch of overlapping areas where it could be potentially ambiguous for a model to decide how to classify, this decision boundary, which is basically the delineation between the red and the blue zones, kind of looks kind of weird like this. Which, if you remember when we talked about bias and variance trade-off the first time last phase, this is potentially overfitting, right? Because who's to say that, like, if we had a data point that ended up like in between these two blue dots over here, what is that going to be classified as? Probably blue, but maybe it's more likely to be red because there's kind of like a clear, smooth line that should go through this. As we increase K and as it considers more of its neighbors and takes some average of its neighbors' classes, you'll see that the decision boundary does begin to smooth. So you see here it's a little bit smoother, like this region over here is a little better. And as you get to K equal to 5 to K equal to 7, you get a much smoother decision boundary. And so with smaller values of K, there is the tendency to overfit, which is also exemplified in this diagram over here, where we have small K, low bias, high variance in your potential outcomes or your predictions, because small value of K is very, very sensitive to changes in the data set. All right, now back to scaling. Oh, before that, any questions about K values? Okay, sweet. The last thing I wanted to talk about was using a scalar and why that is relevant for KNearest Neighbors. So as you can see over here, I used a standard scalar. And if you don't remember, standard scalar basically centers all of your variables at 0 with a standard deviation of 1. Basically normalizes it. It is important to scale your data when you're dealing with KNearest Neighbors because it is computing distances, right? It's computing distances based on your features. So therefore, if you had like a feature that is measured in the thousands versus a feature that is measured in like the 0.1 scale of numbers, you can end up with kind of biased distance measurements, right? It'll be a lot more sensitive to changes in those large numbers than in those smaller numbers. So because of that, it's typical to just scale your data when you're using a distance-based algorithm, not just for classification, but for anything that uses distance as part of its algorithm. Now, where it gets really interesting is once you get more used to doing modeling, which we will over the course of this phase, once we get used to modeling, and once you have an idea of how you want to treat your data, you can actually play around with these distances. So for example, I was doing a project that made use of KNearest Neighbors, and I was actually doing some sort of, doing board game recommendations where if you have a board game, that you know you like, I'm gonna have a data set of board games and basically recommend the nearest neighbors to that one board game. And because I knew that, there are a bunch of features in this data set, things like number of players, genre of the board game, when the board game was created, so on and so forth, I knew that there were certain features that I wanted to be more important than other features. And so because of that, I got to play around with, okay, let's scale some features down to like 0.1 level, let's scale some features up to like 10 levels. And so because of that, it can assign importance to different features based on the scale of those numbers. So definitely not expecting y'all to do any of that at this point, but just be aware that with distance, you do have that freedom and you can like use your creativity and reweight things differently. But for now, just know that especially if you have data that is measured on different scales and different features, you should use a scalar so that it fairly evaluates distance across your feature set. Cool. Questions about that? All right, well, if for whatever reason, this algorithm was confusing or whatever, it's not a big deal. For now, actually, the most important thing is that you understand how to implement one of these models. So pretty much these steps over here, as long as you feel comfortable with what these steps are doing, you're actually fine for the rest of the phase. You'll sort of see, actually, no, you will see that on Thursday and on Saturday as well, we're going to be talking about different models. And yes, I will go through how those models work, but pretty much the same code will apply for all the models we're going to talk about. So I think that's very important to get across. If you can implement first, understanding the algorithms can always catch up later. Cool. Well, that's kind of all I wanted to share for today. Any questions? Jesus. All right. Well, Amir, I saw you come off mute. You had a question?
Yeah, I know. I have a dumb question.
Not the dumb question.
So in the future, I know we haven't gotten to these other models yet, but is it safe to say that if we have a categorical problem, that we can run each of these and the ones that we're going to learn in order to see which one is the best fit? Because we saw like in the past, I think it was like 25, like kind of listing them all out and just looking at the RFC score. So is it safe to do that, or is it kind of like just based off of what type of data you have, and each one is like preferential to, I guess, certain problems?
Yeah, absolutely. So there will be some models that work best with some kinds of data. So for example, on Thursday, we're actually going to see a model called naive Bayes, and it's actually it's just known to perform well on text data for some reason. And these are only through experimentation that these are concluded to do well on certain kinds of data. The topic 31 model is support vector machines, known to do well on smaller data sets with a lot of features. So like kind of wide form data. But for the most part, you can definitely implement any classification model to any like categorical target variable data. And that's actually what the project's going to look like. The project's going to be, you have a categorical data set and you're just going to throw all of your models at it and see which one performs best. So it's kind of a project in automating the modeling process, which I'm going to start to talk about on Thursday. Actually, I'm going to start talking about what that's going to look like on Thursday. And then, yeah, that, and then also evaluating models, which kind of comes hand in hand, like how you can do modeling you can do a bunch of modeling all at once, and you pretty much have all of your results and you just evaluate and then do your business case conclusions, all of that too. So yeah, that's actually exactly what our project's going to look like.
Okay.
Sweet. Any other questions? All right. Well, KNearest Neighbors does not use traditionally what you would call machine learning, but it is a machine learning model. Same for Thursday's model, actually. Thursday's model goes off of the Bayes theorem, if you remember that for Bayes 2. So we're going to talk about that on Thursday. But I promise from Saturdays onwards, those will be machine learning models where you actually use gradient descent, and I'll talk about gradient descent in those contexts. Cool. Well, if there are no other questions, as usual, you can Slack me if you need anything. But yeah, look forward to Thursday. I'll be giving you all that mini assignment on that will be in preparation for the project. So that's what I'll be talking about for the second half of Thursday. And then Saturday, we have one more model. And then next Tuesday is when I'll introduce the project. I'm going to introduce the project a little bit earlier, just so you all have more time to sit with it, get to know what it's all about.
I had a quick question.
Yeah.
For the K values, should you conduct like two models with K equals 1 and then K equals 3 or 4? Is that something that's preferable to do?
Yeah. So I'm actually going to introduce next Tuesday a process we can automate picking the best K. But for now, something like this makes sense, where you just loop through a bunch of values. So let's say you don't need to test 1 through 20. Let's say you just want to do like, maybe you want to do like 1, 3, 5, 7, 9 as a quick example. And you can do something like this. You don't have to plot it on a graph, but you can just take a look at your train and test metrics. Maybe you're a little bit suspicious that like, I don't want everything to be classified perfectly because, you know, it's a little suspicious and maybe overfit even to the test data. So up to you to evaluate. I will talk a lot more about evaluation on next Tuesday when we talk about the project. And also during all of the office hours, I'm going to have a big focus on evaluation in general. But yeah, definitely you would want to test different values of the hyperparameters. That's very much part of the modeling process. However, over this phase, we're going to be talking about, I think, like 9 classification models in total. And so kind of the process it will look like is you're taking those 9 models, throwing your data into all 9 models, and then picking the best 1 or 2 where you actually do this kind of like deep dive into, okay, what's my best K? So I'll talk more about that process next week though. But yes, you ideally want to, if you decide that you want to go with the K-Nearest Neighbors model, you should definitely explore your different values of K.
Thank you.
You're welcome. All right, well, I feel like I spoke super fast, so any questions, please let me know. But if not, I will see you all on Thursday, and maybe I'll see some of you tomorrow as well. All right, bye everybody. Have a good rest of your evening.
Have a good night, guys.
Good night.
Thank you.
Have a good night.